Hi everyone, welcome to Random Thoughts with Alex. In this video I'm going to give you my top 10 favorite popular science books. These are my personal choice of books that I read that I have inspired me or otherwise found very interesting, very useful. And so there's plenty of other popular science books out there that may be better than the ones that I've selected, but these are the ones that meant a lot to me. So I'll start with the number 10. Number 10 is this book here by Ray Kurzweil, The Singularity is Near. So the main reason why this book is number 10 and not rank higher than that is because it's not really a science book. It's more a book about society and futurism. So there is of course science in it, computer science, because that's what the book is about, but that's not really the main topic of the book. So what is the real topic of the book? The singularity that is mentioned in the title is the idea that technology will advance faster and faster and faster until you get to the point where the rise of technology goes vertical. And when you reach the point where the rise is instantaneously, where the succession of innovations is so fast that they're all happening at once, at that point is called the singularity. And Ray Kurzweil is not the first one to propose that such a thing is going to happen. One of the first one was science fiction author Vernor Vinge, who used that concept in some of his novels. Vernor Vinge expected that this was really going to happen, and it would happen sometime in the 1930s. Ray Kurzweil puts that a little further into the future. He anticipates that this is going to happen around 2045, and he describes this as super intelligence, when a artificial intelligence exists that is smarter than the entirety of humanity as a whole, is essentially what it is. So what is the mechanism of this singularity? The idea is like a runaway intelligence development. So if we can one day create an artificial intelligence that's smarter than us, then it stands to reason that that artificial intelligence will be able to create an even smarter artificial intelligence, and that smarter artificial intelligence will then be able to create an even smarter artificial intelligence, and so on and so on and so on. So because it's all computers, we can anticipate that this is all going to happen very fast. Once you reach that tipping point, you get a runaway situation, and what happens after that is completely unpredictable because it's beyond human comprehension. And so this book goes through all the technological innovations that have happened in computer engineering, computer science, and tries to extrapolate from there when we can reasonably expect that such an intelligence explosion is going to happen. And Kurzweil thinks that this will be around the year 2045. Now, Kurzweil is not a nobody. He is one of the main innovators. I believe he worked at Google. He did some inventions there. He's been making predictions for a very long time, and he has a very strong record of making predictions that come to pass. Even his dates of when certain things are going to happen have been very accurate. So if Ray Kurzweil says this, then we should at least pay attention to it. And this idea of the singularity and Kurzweil's uh, predictions of when and how this is going to happen has definitely influenced my thinking about AI and about science and technology and society in general. And for that reason, it's definitely very, very important book. And as I said, the only reason it's number 10 is because it's not really a science book, so that's otherwise I would have ranked it much higher than that. Next, number 9. Number 9 is a book by David Raup, and it's called The Nemesis Affair, or The Nemesis Affair. This book clearly is looks like it's out of print because what's being sold here seems like a used copy. So clearly not everybody agreed that this is a top popular science book, but I thought it was very interesting. And what is this book about? It's about the extinction of the dinosaurs, essentially. So what happened in the 1980s is that people discovered, particularly Walter Alvarez, who is the son of Nobel Prize winner Luis Alvarez, discovered that wherever he went and geological explorations, there was a layer, a thin layer that could be distinguished at the boundary between the Cretaceous layer and the Tertiary layer. So it was called the Cretaceous Tertiary boundary. Now it's known as the Cretaceous Paleogene boundary, and it was dated at 65 million years ago. Now it's dated 66 million years ago, but those are details. So they found this layer, and it had a different colors than the strata above it and below it. And after further analysis, it turned out that this layer had an abnormally high concentration of iridium. Now, iridium is something that's very rare on Earth, but it's not so rare in space. A lot of asteroids in the asteroid belt have high concentrations of iridium. So the hypothesis was posed that this layer was created by the impact of an asteroid on Earth. And by looking at the layers before and after, they could estimate that this would have happened around 65 million years ago. And because this coincided with the disappearance of dinosaurs from the geological record, the idea came that this might have been a meteorite that wiped out the dinosaurs. That was very speculative back then. By now, even years after this book was written, the evidence of this is quite solid, but back then that was a wild hypothesis that not many people believed. So, and the book describes the history of this discovery and all the hypotheses and speculations that happened around it. One of the main ones, which the title refers to as well, is that there was the impression, which is now more or less debunked, but that was still an open question when this book was published in 1999, that there was a recurring of mass extinctions that happened. I believe it was every, forgot the exact number of years, 26 million or thereabouts. So every so many million years there is a mass extinction, and so the question arose, is there something that causes an increased probability of a meteor impact every so many million years? And the hypothesis that came from that was that maybe the sun is a binary star, which seemed very unlikely because we've never noticed a star in the vicinity of the sun. But it could have been a brown dwarf, something like that, a tiny star that is too faint to be observed with the observations that could be made back in the 1980s. And that was still an open question back when the book was published. Now with surveys in the infrared region, we know that there is no such star. We would have found it by now if that was the case. So we know that this is no longer a feasible hypothesis. Also, the timing of mass extinctions, we now have better insights into when those happened, and that periodicity turns out to be an artifact of the information that was available back then. But back then that was still an open question, and it was actually quite interesting to read up on that, and it seemed like a very plausible thing, and that's why that is one of my favorite popular science books. still, despite the things that we know that we didn't know back then. Next, on number 8, we have Innumeracy by mathematician John Allen Paulus. Now, Paulus is a professor of mathematics at Temple University in Philadelphia, and he's written quite a few popular science books and articles about mathematics. And this one in particular, this was the first one that I read, written by him, and I was quite influenced by it because it's something that I can identify with. Innumeracy is the idea that a lot of people, despite being well-rounded and well-educated, don't really have a feel for numbers and don't really understand math, don't really understand numbers, don't really understand probabilities and so on. And this is something I've noticed in my own life, even with scientists, that sometimes scientists come up with hypotheses that I can immediately explain away because the math doesn't work. Sometimes it's very simple to do some couple of quick calculations to see if a scientific hypothesis is plausible or not. And not everybody has that skill. So that's why I identified with this book. And I thought that was quite interesting. One way of looking at it is that if you're non-scientific person, it's perfectly acceptable to have no knowledge of science and math. However, if you are a person who's a scientist or has a scientific or mathematical education, it's a lot less acceptable to not have a cultural education, which is kind of lopsided. And I think there is something to be said for that. I think basic math skills that allow you to quickly calculate if something is plausible or not is a very important life skill that unfortunately a lot of people don't have, and I think we should do more to develop that skill further. And to a great extent, I think we should, when we teach math at school, particularly in elementary school and junior high school, we should pay more attention to practical ways of using not just science, but mathematics, how we can do simple calculations to, like slip of the envelope calculations, to quickly figure out what is a reasonable result for a certain calculation, rather than going through things that are maybe not so interesting for students. So making it interesting by coming up with very practical questions that involve a little bit of math, and then see how we can easily solve these problems with very basic math skills that everybody has. I think that's something I learned from this book, and that's why I think it's been an influential book for me. Next, now we're at number 7. That is the book Faust in Copenhagen by Gino Segre. This book gives us an overview of the early history of quantum mechanics, the first half of the 20th century. And it's a very personalized history, so it follows the main inventors or discoverers of quantum mechanics as real people living real lives, making mistakes, having their own personalities, and that makes this book very approachable and readable to me. Things like a person like Paul Dirac, for instance, who came up with the Dirac equation, the first pioneer in quantum electrodynamics, was a very quirky person, and he gives some anecdotes to illustrate that. For instance, he brought his mother to the Nobel Prize award ceremony, and I mean, Dirac was married and had kids, but it was something that other people would not normally do, but he did because he was that kind of person. He didn't look at what uh, people thought made sense. He just did what made sense to him, and that was not necessarily what made sense to other people. Another character that was described very colorfully is Wolfgang Pauli. He had some he had a very quick wit, and so some of his well-known statements, like if he thought that somebody was really off the mark in a physical explanation, he would say that the person was not even wrong. And that's actually very deep, because that goes back to people like Bertrand Russell and Ludwig Wittgenstein, who figured out that sometimes things can be wrong, but in order to be wrong, a statement has to be meaningful. When a statement is meaningless, it is neither wrong nor right, it is just meaningless. And so that's what Wolfgang Pauli meant when he said that something was not even wrong, it was that the explanation was meaningless. So I thought that was a very clever way of um, critiquing someone. It's a little harsh, but I think that sometimes there can be a good reason to do so. So these anecdotes make this book very approachable, and I really enjoyed reading it, and I learned a lot from it. So that's the next one. Again, it doesn't look like this was a great hit, because I don't think this is a very high selling book. Next, and now we're getting to some more recent books, at least this one. It's still more than 10 years old. The Trouble with Physics by Lee Smolin. Lee Smolin is a physicist who's been studying, doing research on alternatives to string theory, and so this book is particularly a critique of string theory. This is not the first book in this general area in this list. We'll find other ones later on in the list. This is just the first one of its kind that we're discussing. I found this very compelling because I don't understand superstring theory. I'm not going to claim that I understand it, but I always felt like there's something kind of off about it. The idea that we can use a one-dimensional object as a string to describe our world seemed like a strange idea. Now, there's good reasons why this was done, and that is also described, but these ideas, while they were promising in the beginning, just never really panned out, and they were held much longer than made sense, and this is what Lee Smolin was critiquing in this book. Now, the main weakness that I saw in this book, and if that wasn't there I would have been ranked higher, is that Lee Smolin also uses this book to push his own alternative to superstring theory, which is loop quantum gravity. So it's kind of a critique of the competition as a way to promote his own ideas, which, I mean, I understand that he's doing that and he's every right to do that, but I think it does kind of diminish the value and the strength of this book. Next, number 5. Fermat's Last Theorem by Simon Singh. This was a very exciting read for me because I was a undergrad student. I was finishing my chemical engineering degree when the news came that Fermat's last theorem had been proven. Back then, that was in 1993. I still remember it well when I was discussing this with some of my classmates. And we didn't know yet at this time that there were still problems with the proof and that it would take another year to really prove the theorem, but that came later. This book describes the entire history of Fermat and this famous theorem that took 350 years to be proven. So Fermat was a legal person. He had a legal job. He lived in the 17th century, and because of his job he felt that he should avoid contact with other people, to be neutral and to carry out his job in all neutrality. So he took on a job that he could do, a hobby that he could do on his own, and that hobby was mathematics. So he read ancient textbooks on mathematics and started elaborating on them and formulated new theorems and then proved them. And the most famous of those theorems was essentially extending on the Pythagoras theorem, which is the hypotenuse of a triangle. The square of the length is the length of the square of the lengths of the other two sides of a triangle, at least when you have a right-angled triangle. And sometimes this can be formulated with whole numbers. For instance, 3 squared plus 4 squared equals 5 squared. So you have cases where the sum of two squares of whole numbers is the square of a whole number. Now, it turns out that there are no such examples with powers higher than 2. So there is no number set of numbers a, b, and c where a cubed plus b cubed equals c cubed, and where a, b, and c are all whole numbers. And that applies to any term, any power higher than 2. That was first formulated by Louis de Fermat in the 1600s, and then he came up with this idea while reading an ancient textbook, and he wrote in a margin that he had found a wonderful proof of this theorem, that there's no such solution, but that the margin was too narrow to contain the proof. Now, Fermat had formulated multiple theorems and never bothered to write out the proof, because that's how things worked back then. Mathematicians had a tendency to keep their discoveries secret, and they would sometimes brag about what they discovered but never really show the actual math, because they figured that was their competitive advantage to keep that secret. And today, of course, with scientific publications, we have a very different attitude towards proofs, and we only believe that they exist when they're published and when they're peer-reviewed. But back then that was very different. And Fermat had formulated more than 20 theorems, and over the years all of those theorems had been proven by other mathematicians, and all of them were correct, except the one that nobody could find a proof for 350 years. That was the last theorem, and that was eventually proven by a British mathematician, Andrew Wiles, who then worked at Princeton, who's also worked at Oxford, and I believe that's his current affiliation. So it took 350 years. Now, Andrew Wiles used math that didn't exist back then to prove this theorem, so there's reason to believe that there exists a much simpler proof using much simpler math that can prove this theorem, and that is still unknown to this date. And so that's what makes this a very interesting problem. Not only is it a problem that can be formulated very simply, but there is reason to believe that there is actually a relatively simple proof that has eluded people for, by now, almost 4 centuries. Now, the book describes the entire history of all the attempts that have been made over the centuries to prove this theorem, and there's been some very colorful people who worked on this, and the lives of these people is amazing. So that's actually one of the strengths of this book, is to read about all these amazing mathematicians who, besides mathematics, had some very colorful lives and of their own. Let's go to the next one. This is number 4, Lost in Math by Sabine Hossenfelder. Now, Sabine Hossenfelder is a well-known science YouTuber, so it's always nice to be able to promote a fellow YouTuber. Sabine Hossenfelder is a physicist who's worked on fundamental physics and has over the years become more critical of the field of physics and how it's been exercised. So in this sense, this book is very similar to the book of Lee Smolin that I talked to earlier that was ranked number 6, but I feel that Sabine's book is better, partly because she's not plugging her own theories, but actually just explains why she thinks there is a problem with physics, and what she sees as the problem is that physicists are using beauty or mathematical elegance as a criterion for evaluating what is a promising avenue for solving some of the unsolved problems in physics. And she believes that that's just not an appropriate way to do science. Science has nothing to do with beauty, it has to do with truth. And of course, she's absolutely right about that. The reason why people use beauty as a criterion in science is because this has worked in the past. And take Einstein, for instance. He's used elegance and beauty a lot in developing relativity, and so people are still doing that because they're highly influenced by Albert Einstein. But maybe they should try something else. If this hasn't worked for the last 50 years, then maybe there's reason to believe that the actual solution to problems is going to be found somewhere else. I think this has been a very interesting read. I've really enjoyed reading this book, and I enjoy watching Sabine Hossenfelder's YouTube channel. So if you're not following her, I strongly recommend that you do. It's definitely worth your while. This brings me to the next one. The Emperor's New Mind by Roger Penrose. Now this book does hint upon some of the issues that we talked about in the previous book in passing, and I think that's why it's useful to have them side by side here. The Emperor's New Mind is the idea, it develops the idea that to explain consciousness we need something beyond our current understanding of physics. And in order to argue that, Penrose gives a complete overview of all the fundamental science that exists and try to evaluate if any of that science can explain consciousness. And he comes to the conclusion that you can't, and that we will need to find new principles, particularly in quantum mechanics, to explain consciousness. Roger Penrose is a mathematics professor at Oxford, and he won the Nobel Prize years after writing this book for his contributions to general relativity. That was when gravitational waves were discovered experimentally. That's when Penrose was also honored with the Nobel Prize, in addition to the people who made the experimental work done. But back in 1999, that was not happening yet. Now, what I found really interesting in this book was that he tried to categorize different scientific theories based on their status, how well established they are. And he had a category in there that was tentative. So certain theories he felt were tentative theories, and he wrote in a footnote that he did that out of politeness because many of his good friends were doing these theories, and he would have preferred to call them misguided, but he didn't want to get into trouble with his friends, so he decided to call them tentative. At least he had the honesty to explain all of that in the book. So, uh, but this was kind of the first indication that there was a fundamental problem in physics. So as you can see here, this book was written in 1999, so that's about 8 or 9 years before, 8 years I think, before Lee Smolin wrote his book. Uh, so he was one of the very first critics of string theory, uh, even though he was very polite about it. And to me, that definitely influenced me in my thinking about physics. Next, number 2, is this book, A Short History of Nearly Everything by Bill Bryson. Now, Bill Bryson is actually a travel writer, and one day he decided, instead of writing about some trips, he wanted to write about science. And I believe he spent 3 years studying science and the history of science, and then wrote a book about a very big, comprehensive book. And the result is quite amazing. It's very accurate, even though Bill Bryson is not a scientist himself. He really took the trouble of learning this material very accurately, and he describes it very well. And because he's a very experienced writer, he writes very fluently, and he adds a lot of anecdotes. He knows what kind of anecdotes he needs to add to make this otherwise dry material much more palatable, much more interesting to read. And have at occasions used some of the anecdotes that he describes there in my own lessons to kind of make my own classes a little more interesting. And that's why it's such a highly ranked book in my list, despite not coming from an actual scientist. And then number 1, to me this is like the mother of all popular science books, and that's the book by Albert Einstein himself, Relativity, the Special and General Theory. So shortly after Einstein developed general relativity, he wrote a popular science account of the special theory, which he developed in 1905, published in 1905, and a general relativity, which he published in late in 1915, and which he had worked 10 years on with lots of dead ends and trying again. And the history of general relativity is quite interesting in and of itself. Now, this book is quite well written, although the translation is a little awkward for the most part. It was written originally in German, but he's using very interesting rhetorical devices to get his point across. And in a sense, I would also see that as a bit of a weakness of the book, is that it's almost deceptive in how he really sets up his argument to lead the reader to think the way he's thinking, and deceptive in the sense that he kind of steers away from ways of thinking that could lead to a different conclusion, because that's the thing with relativity, particularly with special relativity, is that ultimately special relativity is like how should I say that, a formalism. It's a set of conventions that are made, and it turns out that as long as you follow these conventions, you come up with a theory that is not only self-consistent, but is also consistent with every measurement that's ever been made. And that's the real strength of the theory. It's not that this is the only way how to describe reality, because before Einstein, Hendrik Lorentz had developed his own version of relativity with the Lorentz transformation, and the Lorentz transformation is essentially equivalent mathematically with special relativity. It's just that it uses the concept of absolute space, which you can never actually measure experimentally, and that was Einstein's whole point. He said, well, if we can't measure it experimentally, it should not be in our theory. So he went out of his way to avoid using any concept of absolute space in his theory, and that's the power of his theory. He got rid of the elements that are essentially metaphysical. But that doesn't mean that this is the way space really is. There may well be an absolute space. It's just that it's where the existence is a metaphysical idea, maybe a true idea, but metaphysical nonetheless, and that's why it isn't there. Now, Einstein, despite writing this in such a way that the ether, the absolute space, is not there, Einstein didn't prove that the ether doesn't exist, even though that's how people often perceive relativity, that Einstein has proven that the ether doesn't exist. No, he has proven that you don't need the ether to explain anything in physics, that it doesn't have any explanatory power, that you can write physics entirely without using the concept of an ether at all. That's the innovation that Einstein had with special relativity. But he was not even sure himself whether the ether existed or not, and there were times when he actually believed that the ether did exist. And of course, towards the end of the book, he describes general relativity, although in a lot less detail than special relativity, and then ends the book with some ideas about the cosmos as a whole and how that fits in with general relativity. So if you haven't read it, I would strongly recommend that you do. It's actually quite an interesting read if you're willing to take the effort, because it does take some effort to get an understanding of this book. But to me, this is the most influential, the best popular science book ever written. And that concludes my top 10. I hope you like this video. If you do, please like this video and subscribe to the channel, and I will try to come up with more of these videos in the future.